This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
You get 100% efficient, so you don't have any heat dissipation near power supply, but you always got heat dissipation. You are losing energy when you are converting. So then people might ask, we studied linear regulator, we studied shunt regulator, why do you need switching mode power supplies? Majority of electronic DC loads are supplied from standard power sources. Standard source voltages may not match the levels required by the microprocessor, motors, LEDs or other loads, especially when the source voltage is not regulated. So in your case also you have different types of requirement, 3.3, 5 volt, different voltage levels. Linear regulators which can only step down as input. Linear means both the regulators, shunt or linear, these regulators can only step down. Your output voltage will be always less than the input voltage. SMPS, switching mode power supplies, also called switching mode power supplies. SMPS are attractive because a topology can be selected to fit nearly any output voltages. You can step up, you can step down, even you can invert. Invert means you got plus 5, you want to make minus 5. So these things you can do using step SMPS, switching mode. Nowadays 12 volt V in, 3.3 V out switching mode synchronous buck step down supply can usually achieve 90% efficiency. See, when you are using, which is efficiency versus less than 27.5% from a linear regulator. So if you are designing a linear regulator, your efficiency is only around 27.5. Say take it as 25. If it is 25 means when you have input voltage here, as I said, 10 volt 1 amps. So when you are designing a linear regulator, the problem will be the following. So in this case 10 volt 1 amps equal to 10 watt. Then you got only 25% efficiency, remaining 75% is lost as heat. Then how much maximum you can get here? If you are using 5 volt, how much current you can get? So 25% efficiency means you are getting only 2.5 watt. So here you can get only 0.5 amps, see, because of the efficiency. So efficiency is very important. But in switching mode power supplies, that's the reason switching mode is very important. You can get 90% efficiency. So that's another advantage. Switch mode power supplies, SMPS, an efficient method for voltage conversion. 240 volt to 5 volt mobile phone charger, they are using switching mode. 5 volt to 10 kilovolt backlight, they are using RS232, they are using step up. 5 volt to plus or minus 10 volt using SMPS. I think this is a mistake, I think here 10 volt here, 5 volt to 10 volt backlight, so I will remove the K. Good that you found out. But then having said that, this is a simple design that will give you 5 volt to 10 volt, but then you can step up to big voltages with some special kind of stepping up. But then here the backlight is definitely not K, this is a V, only 10 volt. Then that is another good question. So you might go for the interview, somebody will ask you, can you step up into kilovolt? Think about it. Good that you asked that question. So you have to email me.
So unless you're using a transformer, because you require very heavy insulation, sir, for 10 kV, the insulation requirement will be so large that electronics, it doesn't make sense.
So how will you step up? Because they might ask you, because you studied about the regulator, and then if it is in kilovolt, no, it's not. This is a serious question. Somebody can ask you. So he already partially answered my question, but then you can also think of and then let me know. How can you step up to kilovolt? Because these are about stepping up, stepping down. Can we do that one? Yeah. So here it is. I will remove the K. So this is for the backlight. But then that is good that you pointed out. So people can ask you a question. How will you then step up to, suppose your requirement is in kilovolt? How will you do it? So buck converter or step down switching mode supply. So here I already explained, you got a voltage V in, and then this is your MOS, then you got a zener, then this is an inductor, and then this is a capacitor. So what will happen is then you are going to connect a pulse on off to the your MOS transistor. The on and off states of the MOSFET drives the switching mode power supply circuit into two phases. So when you have this on and off, you have two phases. One is a charge phase, another one is called a discharge phase. This charge phase and discharge phase are there because of this inductor. So when it is on, inductor charges during on period of the MOSFET. So this inductor will charge. So that is the reason it is showing. See, inductor is charging through this path during the on phase. So that's what I have drawn like this, and it is coming and then it is closed here. So the circuit should be closed. So this is a one charging phase. So inductor is charging through this way when this one is on. So that is called charging. Inductor is charging. During off state, inductor opposes the change in the current, and hence a back EMF is developed with a polarity opposite that of the power supply source. So when what will happen is initially it is charging, this will be positive, this will be negative. But then when you are switching off, when this is off, what will happen is inductor will reverse the polarity. That's what is shown. This will become positive, this will become negative, and then again it will discharge through this way. And then this time it will be completed like this. See, that's the discharge path. So this is during off time, this is the path. And then energy stored in the inductor is transferred to the output load and the capacitor during the discharge phase. Discharging path is through the diode. So discharging path is through the diode because it should be closed. So whenever there is a charging, discharging, it should be in a closed path. So that's the reason this is one path and then this is another path. So if you add then, so this is on here. Here you can see there is no feedback. So if you connect a feedback here, sense control, then you got a step up converter, because this is called a buck converter. So you can step up the voltage using this way. So as I drawn previously, it's very simple to understand. So you got a power supply. So you got a 5 volt. Then you got a MOS. So it's an NMOS, and then you are going to have a zener, then inductor, then a capacitor, then this is your RL, your load. Then this is on, this is off, this is on. So during on phase, what will happen is this is on. So during the on phase, this will be on. Then what will happen is your voltage is going like this, and then it is charging the inductor because this is reverse biased. So initially this will become positive, this will become negative, because here it is positive, so that is the reason this will become positive, and then inductor is storing the charge, and then the path is completed like this. Then when during off time, when this is off, then this is off. So you are cutting off 5 volt from the inductor. Inductor doesn't like. So what will happen is inductor will discharge it. So then it will reverse the polarity. So this will become negative, this will become positive. And then the inductor will discharge through like this, through this inductor, because this is a zener, this is a positive. So that's the reason this is positive. It will come and finish it like this. So during on and off, you are getting a current. So when it is discharging, some current also will go through this one because of the load, because depending upon what you connect here. So during on phase and off phase, you are getting power. And then if your on phase is, suppose I am going to connect here, I am going to go number 1. You are going to connect something like this. So what is the output voltage? No loss. Yeah. So if it is ideal, no loss, your output is 5 volt. Now what I am going to do is I am going to switch it on, then going to switch it off after a long time, like this. It should reduce. But then if I am going to increase the frequency, yeah, because then it is you are so you are getting one voltage, then you are again discharging. When you are switching off, it will again discharge it. So yeah. So that's how it works. So when you connect a sense, but then here previously, when you come to this one, you will understand. Here what will happen is in this case we discussed, but then there is a catch. I did not say that this will increase or decrease. So here it is on, and then this is constantly on, no loss, you may get 5 volt, and then this case is question mark. So here it is, the time is more, and then you said that your answer is less than 5 volt. Then my question is, I am going to increase the frequency. So this is the buck design. So I am going to increase the frequency. So there are 3 answers possible. The answer number 1, 5 volt. Answer number 2, less than 5 volt. Answer number 3, more than 5 volt. I'll give you 1 minute. When I am making it pulsed, when the frequency increases, will I get 5? No. So then we'll come back. So my question was, this is a buck converter. In the buck converter, so why do you need this type of switching? So when this is on, you can get a 5 volt. When I am making it pulsed like this, then what will happen is my output also will be, so then during the on phase you are getting it will discharge, then your off phase also it will discharge, then your on will happen after some time. You know what I meant? So that it will be definitely your output will be less than 5 volt. Obviously your output also got some kind of fluctuation, then you will be using some smoothing circuit later in the switching mode. But then when you make it this one, how many of you think it will be more than 5? Nobody. Okay, you. Then you are then less than 5. 5. So how you can get more than 5?
So initially, like during this condition, your inductor gets charged, and when you are switching it off, while it's discharging, you again switch on. Because of the increase in frequency, you see that your voltage will slightly increase.
Yeah, but then even if you are keeping it constantly on, you can get only 5 volt. And then when you space it, what you are doing is you are switching on and off, you are controlling. But during switching off also you are getting, but then the question is this is a maximum you can get constantly on. So when you make it pulsed means what you are adjusting is you can adjust between 5 volt and maybe 1 volt, that range. You can step down. So you can't step up using this configuration. How can you step up? Because when it is constantly on, you are getting 5 volt, and then you are controlling the switching so that you are charging then discharging. Definitely when you average it, then when you have this type arrangement, what will happen is your output also will be, so when you have 2, then your output also will be something like this. After you will be connecting some smoothing circuit, and then you will be taking the average of your output. So your output will be definitely it will be less than 5 volt. And then here you may get maybe 4.5 volt, something like that. So then buck means in this configuration you are using a switching mechanism to step down. So that's the reason we are using a switching mode. So this can precisely step down, and then you are using some pulses. But then the problem with the pulses is this one got lots of efficiency. So that's the reason this step down, buck step down is much more efficient than your linear one. But the disadvantage is because you have got some switching, you may have some switching frequencies in your circuit. It can couple, so that anyway you don't have to worry. Most of the time these guys will put some filtering so that switching will not affect your circuit. So then this one is a stepping down mechanism. Then when you connect when you are using only this way, you are stepping down, but then you don't have feedback. So if you can put feedback, then you got a buck, then you are a buck converter. So how will you incorporate the feedback? Same way. So we will be using the resistor, and then you have got your op amp, then you got the error signal, then the error signal, then here you need one more addition, that is a variable pulse width modulator, because the error signal you can't connect directly here, because error signal should control the pulse width of your signal, because your interest is varying the frequency of switching on and off, and then that you want to be controlled using some error voltage. When the voltage is when the voltage is more, so when you connect I will come back again. So when you connect a sense circuit here, then you are putting a feedback to the buck converter. So when you are connecting a feedback, then you will be connecting something like this. So I'll talk about the feedback first. The feedback is our normal feedback using 2 resistances, and then you got an op amp. Then the error signal, usually we can't connect directly here because this is a switching mode. Error signal is usually a DC voltage, and then we need some variable pulse width modulator. The duty of this one is, depending upon some input to DC voltage level, this will vary the frequency of your pulses, the switching pulses. And then if you connect something like this, then we can explain. So pulse on, when the pulse is on during the positive cycle, pulse is on, what will happen? Here you got the V in and the pulse on. So this is a positive pulse, then this MOSFET will be on. When the MOSFET will be on, I have shown the arrow, and then this here you get the positive voltage, but then because this positive voltage, this inductor will be off, and then inductor this side will become positive, and then the inductor this side will become negative, and then mainly it will go through this capacitor. Definitely some current will be going through the load depending upon the load, and then some current also will be going to the feedback. And then so the charging path is usually the main current will be flowing from here and then through the inductor and then coming to the capacitor. So inductor charges during on period of the MOSFET through the capacitor, and the diode is reverse biased. During off state, inductor opposes change in current. So during off state, what will happen is the inductor will oppose this change in current, and hence a back EMF is developed with the polarity opposite to that of the power supply source. So that polarity will reverse. Energy stored in the inductor is transferred to the output load and the capacitor during the discharging phase. The discharging path is through the diode. So then when it is discharging, the discharging path is through the diode. This will become positive, this will become negative, so that it will be discharging like this. So during the off phase, this will happen. So when it is off, the inductor will reverse the polarity. This will become negative, this will become positive, and then what will happen is it will be, so this is a positive, this is a negative. When this one become negative, what will happen? This diode will be on, then it will be discharging like this. See. So inductor charges during on period of the MOSFET through the capacitor and diode is reverse biased. During off state, inductor opposes the charge in the current and hence a back EMF is developed. So that's how during pulse is off that will happen. So linear versus SMPS. So when you check linear versus SMPS, see the additional stuff is using an inductor, one diode and a capacitor. Then you got a variable pulse width modulator. So when you are using this way, then you are getting a much more efficient way of stepping down, and then you are getting very high efficient converter. So output voltages. So the output voltages, see, this will divide you. Ideally, the output voltage is expressed as V out equal to T on divided by T into V in. You know what I mean? See, T on divided by period of the pulse into V in. So that's the reason I will go back to the previous question. So your V out. So here V out equal to V in into T on divided by time period. So time period is from here to here, from this point to this point. That is a time period. T on, that is this on period. So then your output voltage equal to V in into T on by T. So that's the reason how much maximum you can get here. Your T on, which is equal to capital T, that is this one. So that is the reason you can get a maximum V out equal to V in. Then by using this T on by T, you are reducing the T on time so that you can step down the voltage. So coming back to the slide. So ideally the output voltage is V out equal to T on by T into V in. T is the period of the on off cycle of the Q1 and is related to the frequency T equal to 1 by F. The period is the sum of the on time and the off time. T equal to T on plus T off, because that is a period. T on by T is also called duty cycle, because sometimes people use the duty cycle in some textbook. That is T on by T.
Sir, why is the inductor used in this case?
Sorry?
I could just use a switch and just switch on and switch off and I can get my average voltage reduced, no sir. So is the inductor for filtering or does it serve any purpose to reduce the voltage?
So when you are switching on and then switching off, then yes, then what you are doing is when you are switching on,
We get full voltage.
yeah, full voltage, but then you are
Go to zero.
then you are getting on, and then that one when you take a average, you don't get that smooth DC.
To smoothen out.
Yeah. But then when you have an inductor, but then there is another problem. Then your efficiency will be very, very less, because you are getting only 5 volt during that little bit current. Then again you are getting off, means nothing is going. So that way is very, very less efficient. But then here what is happened, there are two reasons. So answer to your question, first one is when you are switching completely on, then you use just a switch on, then you are switch off. Yes, you can make average voltage will be less, but it's very, very inefficient. And the second one is smoothing also will be very difficult. When you are using inductor, you can see that inductor is charging, and when it is off, again you are getting a charge. So on period you are getting a charge, off period you are getting a charge, because the current is flowing, so that is less efficiency is very high. The other is good way of thinking. So variable pulse width modulator. So if you don't know about the variable pulse width modulator, so what it does is error signal. So when you have some voltage here, so this is a variable pulse width modulator. So when your voltage is some kind of constant, the pulse is something like this. When the voltage is increasing, means if your error voltage is increasing, see, if this input voltage is increasing, then what will happen is, see, the width will decrease, width will increase. So this is called a variable pulse width modulator. So example is LTC 6992 is a variable pulse width modulator. So analog PWM duty cycle control 0 to 1 volt. Using 0 to 1 volt, you can vary the pulse width or the duty cycle. So that's how. So this one is needed here, pulse width modulator, because here you are getting a DC voltage, varying DC voltage depending upon the feedback. This may be less or high depending upon this voltage is going back up or down, and then you can get the feedback. So SMPS output voltage. So this one again will answer your question. So when the Q1 is on, then your V out, VDC will increase. and then when it is off, again the current will decrease, but it will not touch the 0. So that you can see little bit fluctuation. And V out depends on the duty cycle. When the duty cycle is very high, you can see that this will be on for more time, off, then it will be discharging, something like this. When the duty cycle is off, duty cycle is very small. T on is very small, means you are getting less than 4 or 5 volt. If your input is 5 volt, you might be getting maybe 2 volt. That's how we are controlling. So SMPS output voltage. So this is a design. So you can see that here you got 12 volt, and if this one equal to 3.9 volt, if you are using a Zener, 3.9 volt, and then this will be 3.9 volt, and if this is 3.9 volt, you can get maybe 10 volt here. How can you get 10 volt here? Because you got two variables. One is you can arrange R1 R2 in some way. There is also another control that is using V on. So you can vary the duty cycle. That also will give you the voltage here. So then previously by varying R1 and R2 you got some voltage here. Now you got one more parameter, that is a pulse width. That also will decide what is the output here, the voltage. Now how the feedback is working in the SMPS. So in this here, what we did is, here we got 12 volt. By varying the pulse width, here we made it 10 volt. We have chosen R1 and R2 in such a way that, and the pulse width, everything we have chosen, so we got 10 volt. So this is the design. So your input is 12 volt, your output is 10 volt, then you are using a Zener diode of 3.9 volt. And now we are going to study how the feedback is going to work. Suppose 12 volt reduced to 11 volt, then what will happen? So when 12 volt reduced to 11 volt, then what will happen to the output voltage? The output voltage will, what will happen? When the output voltage will reduce. When the output voltage is reducing, what will happen to this voltage? V constant here, this voltage. Increase or decrease? So this will increase. When this is increasing, what will happen to your duty cycle of your pulse width variable? So when the voltage is increasing, when the voltage is increasing, what is happening? Your duty cycle is going to increase because your on time period is going to increase. When the voltage is increasing, when the on time period is increasing, see previously this was this much, so it will increase. When the on time period is increasing, what will happen to this voltage? When on time period is increasing, VO equal to TON by TS into Vin. When the on time period is increasing, what will happen? This voltage will increase, and then again it will be 10 volt. Again vice versa. If this voltage is increasing from 12 volt to 15 volt, then what will happen is this voltage will increase. Output voltage. When the output voltage is increasing, this voltage will reduce. When this voltage is reducing, the on time period will decrease. When on time period is decreasing, then your output voltage again will decrease to 10 volt. So that's how it works. So feedback circuit adjusts the width of the pulses to keep the output voltage constant. So these are the two cases. When the input voltage is decreasing, then this one will increase, and then it will increase on time period, and then output voltage will come back to the original one. When the input voltage is increasing, then what will happen is your output voltage will increase, then this error voltage or V constant, here I have written V constant or error voltage will decrease, then that will decrease the pulse width. So that again this will become your normal, back to the normal voltage. The feedback circuit adjusts the width of the pulses to keep the output voltage constant. Now we are going to study the boost converter. So now we studied buck. So buck converter, please remember buck means a stepping down. But then why do we need that stepping down? Because we got linear and shunt. that can also do step down, but the linear and shunt got poor efficiency around 27%, but in switching mode you can get around 90% efficiency. Then switching mode, another advantage is you can get a boost. See, boost converter. Boost means from the name itself we know that it can step up. So step up is called boost. Then how it can boost? So this is a step down buck converter. So this is a step up boost converter. So if you see the diagram, it's only rearranging the components. So if you got the components for step down, you can also make for step up. Just rearrange it. So how are you going to rearrange it? Then how can you step up the voltage? So when this is on, so this is the input voltage, then here you will be having the inductor, and then here you got the MOS, and then you got the diode here, and then capacitor here. This is your load. Inductor charges during on period through the least impedance MOSFET, because when inductor is charging, when the MOSFET which is on means then this is the least impedance. That's the reason when this is on and then inductor is charging through this least impedance MOSFET. So this is a charging path. See, on time during on period, so this is charging, inductor is charging through this way. When it is off, when the inductor is off, sorry, when the MOSFET is off, when your MOS transistor is off, what will happen is the inductor will reverse the polarity, and then this will become positive, and then this will become negative, and then that will be discharging through this capacitor, and then all the way like this. And then when it is discharging during off state, inductor opposes change in current, and hence a back EMF is developed with the polarity opposite of that of supply source. The voltage sources are in series with the load within the V in plus VL, and hence boost the output voltage. So how can you boost the voltage? So when you are boosting the voltage means your current means you can add some current line. Voltage means you need, suppose you got a 2-volt battery, then you want a 4-volt, then you need another battery to be putting in series, then only you can get a 4-volt. So whenever you are stepping up, you need something like that. Your input is 5-volt, then if you want 10-volt, you need something in series. So that's how the inductor is doing the trick. So I will draw it so that it will be more clear. So far we discussed this buck converter. So I will write step down. So this is a step down topology, that is a buck. In the buck again we are using an inductor for charging and discharging, and then using buck converter we can step down. Using the same components we can make a step up. So how can we make a step up using the same number of components? In the step up we have got again the input. So this is your V in, and then here the difference is we are going to connect inductor first, then this is your MOS. So this is the MOS input, and then this is the ground. Then from here we are going to put that center here, and then you got a capacitor, ground, then this is your load. So during on phase, this is off. So on phase, what will happen is when this is on, then this is a V in. Okay, maybe that may be 5-volt. So during V in 5-volt, so this is connected to the positive. So inductor will become positive, this will become negative, and then the current will be flowing like this, and this is the least impedance path. So that is the reason the inductor will be charging like this during on phase. So inductor will be charging through the least impedance path is this one. So that is the reason it's charging. But during off phase, what will happen? When this is off, so this is on. When this is off, the inductor doesn't like change in the current. So inductor will oppose the polarity. So this will become negative, this will become positive. You know what I meant? When that will become negative, this will become positive. What will happen is then this inductor will discharge, because this is off. During off period means this transistor is off. Then the inductor will discharge through all this way like this. When this is discharging, somebody is measuring the voltage between this point and ground. So what will be the voltage between this point and ground? So that should be V in that is equal to 5 volt plus we need to take into account another voltage. What is that voltage? Sorry? Yeah, so this inductor, because inductor is, this is positive, this is negative, this is negative, this is positive. So that is connected, that is like you got a battery, so this is negative, this is positive, and then you are putting another battery here. See, this is negative, this is positive again. So if this is 2 volt, this is 2 volt, then when you measure between this point and this point, you are getting 4 volt. Same way, this voltage, see this voltage and this voltage, when you are measuring between this point and ground means this point and ground. So when you measure like this, you are getting 5 volt plus whatever the voltage in the inductor. So that's the reason you are getting V in plus VL. So VL is the inductor voltage. So that's the reason you are getting a stepping up. You know what I meant? So now you are getting, you are creating another source in the inductor. So inductor is acting like a cell for some time. So that's how you are getting a, so you can boost your voltage. If it is 5 volt, ideally maybe you can get another 5 volt here. You will not get it, but then it will be more than 5 volt. So greater than 5 volt is possible. So this is a, that's how you are stepping up.
Excuse me, why greater than 5 volts?
Sorry?
Why greater than 5 volts is possible?
Yeah, because ideally you can get 10 volt, but then your efficiency is not 100%. Using the inductor when you are discharging, inductor should give you maybe another 5 volt. That is not possible. Your output will be less than 10 volt maybe. You can't get more than 10. Yeah, it will step up maybe 5 to 8 or 5 to 7.5 depending upon the efficiency. Then boost converter, again boost converter also same way. The feedback is same. See, you can see feedback is same, and then the components arrangement is only different. Then you are making a boost converter with feedback. And then boost converter, how it will be working? See, this part is only rearranged. When you see the buck converter, your inductor is moved to this side. So if you go up, see in the buck converter, if you move the inductor to this side and then you connect your diode in series, then you got a boost converter. So in the boost converter, how it will work? When pulse on, when the pulse on means when you are getting a, this is on, then what will happen is initially VL jumps into V in when Q1 turns on. When turns on, when this is on, when your transistor, most transistor is on, a voltage equal to approximately is induced across the inductor with a polarity as indicated above. So just switch it on, what will happen is this will become positive, this will become negative, and then because this is negative, this will become negative, this will become positive. During the on time of the inductor voltage decreases from its initial maxima and diode is reverse biased. See, that's the reason the diode is reverse biased. No longer is on, the smaller becomes, because this is a negative charge. So the diode is, this is negative, this is positive. Because diode, if it is should be on, it should be other way around. So that is the reason your charging will happen. See, so this will be positive, this will be negative, and then the diode will be not on. During the on time, capacitor only discharges an extremely small amount through the load. So when it is on, the capacitor also, here the capacitor, when this is positive, it will discharge only a small amount. Then what will happen is when the pulse is off, so first we will check the pulse is off, then again we will go back. When the pulse is off, when turns off, as indicated above, the inductor voltage suddenly reverses the polarity, see, and adds to the V in. See, this is the V in. So now this is positive, this is negative, this is positive. So it is adding on, forward biasing the diode D1. So this diode also is forward biased now because this become positive, and allowing the capacitor to charge. See, now the capacitor will be charging. So then what it says is, what from this one, when the diode is, now we will go back. When the pulse is on, what is happening? This will become positive, this will become negative. And so this will become negative, this will become positive, so that the diode is off. When this is on, so basically what is happening is the charging is happening through this MOS. And when it is off means, then what is happening is the inductor reverses the polarity, and then when you measure between this point and ground, so this point and ground or this point and ground both are same, then you are getting this voltage plus the voltage across the inductor, because that is coming in series. So that's how you are getting a more voltage. Then buck boost converter or voltage inverter. So using the same mechanism, you can also invert the voltage. So now you learned how to step down, then you learned how to step up. Now you want to invert the voltage, means you got a positive voltage, you want to invert it. So how can you invert the voltage? So using this topology, again by rearranging, you can invert the voltage. So in order to invert the voltage, what is required? Inversion means maybe during one cycle you may get a positive, but then when you are getting the output, the current should be in the reverse direction. So if you can make current in the reverse direction in the output, then you can get a negative voltage. How do you get a negative voltage? You make the current reverse. So this configuration can invert it. How? So you got a voltage, input voltage, and then during the on state what will happen? So this is positive, then this diode is going to be on. This MOS transistor is going to be on. When this MOS transistor is on, then this positive charge, but then what will happen is this diode is here, this is a positive, so that this will be off, and then this charging will happen through the inductor. So that's the reason during on, the charging of the inductor will happen like this. When it is off, what will happen is inductor will reverse the polarity and will discharge through this diode, and you get a negative. So how can you invert it? See, I will draw it. See, I want to invert a voltage, so I want to make maybe plus 5 to minus 5 or something like that. So I want to make a inversion. So if I want to reverse the polarity, so what I need is I got an input, and then I got a MOS transistor, okay, and then I got an inductor. Then I will be putting a Zener diode, and then I got a capacitor. Then this is my load. So this is arrangement. So then I am going to connect pulses like this, and then this may be 5 volt. So during on phase, so when this is on, what will happen? When this is on, your MOS is equal to on. When this is on means this is on during the positive cycle like this. When this is on side means this positive, see this is a positive is coming through, the current is flowing, and then here it will be positive. So that this diode is, so when this is positive, what will happen to the diode? Off. So you don't get anything output. And then so your charging will be from here through this one, and the inductor, something like that, it is completed. So this will become negative. So that is the on phase. When this off phase comes, what will happen is inductor will reverse the polarity. So this off phase, inductor will become negative, this will become positive. That is during off phase. So this is during on phase, this line. So this is off phase. Inductor, this become positive, this become negative during the off phase. Then what will happen? When this become positive, what will happen is this inductor will discharge like this through the diode like this, because now this become negative, this become positive, so that your current is coming from the ground to some point, see, like this. So the current is coming from the ground means then you are getting a negative charge. It's like symbol. You got a resistor, when the current is like this, you are getting plus V, because current is going through like this to the ground. So this is the current. When the current is coming like this, then what will happen? Minus V, because from the ground, if the current is coming that way, you get negative voltage. Same way, when the inductor reverses the polarity, this will become positive, this will become negative, then this diode will be on, because this is a negative voltage, and the inductor will be discharging like this, so that you are getting a negative. You know what I meant? So that's how you are getting an inverter circuit. Again, buck boost converter or voltage inverter, same way you can connect your pulse width modulator and feedback circuit. And when it is on, you can see on means this MOS transistor is on, and then what will happen is when it is on, the positive is coming, and then this inductor, it is charging the inductor. Because this is positive, this diode will be off, nothing will go through. So the during on phase, the inductor is charging, so you don't get anything here. But during off phase, what will happen is inductor will reverse the polarity. So this is positive, negative, inductor will reverse the polarity when this is off. When this is off, then what will happen is this will become positive, this will become negative. In that case, this diode, this is negative, and then this positive, and then this ground is connected to this ground, so that it will be discharging through like this, through the diode. So that you see from here, when you take this point, the current is coming from the ground. So that's the reason this side is negative. And then the feedback will work in the usual way. This is the feedback. When your output voltage is increasing, this voltage will increase, and then it will be adjusting the pulse width. The feedback will work in the normal way. So then now we learned buck, then boost, then buck boost. Buck boost means an inverter, and the feedback is common to all the circuits. For the buck boost and buck boost, the feedback, the topology is same, variable pulse width modulator. So by varying the pulse width, you can adjust your negative voltage. So buck, that is step down, boost, step up, buck boost, inverter. So these three topologies are possible. Examples of boost, step up converter. So this is a ADP 1613 is a switching mode supply, where they will provide you the IC, you can connect some external components, and then you can see efficiency. So they will provide efficiency versus load current. And then they say that switching mode, that is 1.3 megahertz. So that is a switching, and then this is the efficiency. So if you are operating at around 100 milliamps, then you get 90% efficiency. But if you are operating at low current, you don't get that much efficiency. When it is around 100 milliamps, so they will say this is the range you get very good efficiency. Switching frequencies. Then what are the problems with the switching mode supplies? Can dramatically improve or reduce the noise within your sensitive circuit to understand the switching frequencies of DC-DC converters, and make sure that they are either outside the frequency range of your system or adequately filtered with the tailored LC filtering. Means problem with the switching mode power supplies, when you have some sensitive circuit, you have to be careful, because this type of switching, that switching frequency can couple to your power supply or the ground plane. It will affect the performance. So you need a better filtering. And so that's all about power supplies. So for the power supplies, we learned about linear power supply, and under linear power supplies we have got linear and shunt, both are step down. Then we studied switching mode power supplies. Switching mode power supplies, we studied buck, boost, step up, and then buck boost inverter. Then we also studied, when we studied all these power supplies, we also studied the concept of feedback, how you can incorporate the feedback to make sure that the voltage is constant. And then we will continue in the next lecture the remaining portions. So I think we are pretty much near the end of the syllabus for the electronic system design. See, you don't have to study much, only all the basics, once you study. But the only thing is, so we will be going, I will be going through some of the questions as well, because we got time, and then I also will be teaching you some non-examinable material that will involve some communication protocols like I2C, SPI, those stuff.
I'm really confused about this direction. This direction. It's the current. It's not the current direction, I think.
Yeah, that's the direction of the current.
Why? Because at first this inductor will oppose the change.
No. So when the pulse is on,
Yeah.
when the pulse is on, so this is a positive voltage. Maybe here you are connecting, say 5 ohm.
Yeah.
Then this is the positive side, isn't it? So when this is on,
Yeah.
then the current is coming. This is a positive. So that's the reason this is a positive. And then when this is positive, this will be negative.
Yes.
And then and then this is charging like this. Okay.
Yes.
And then when this is off,
Yes.
when this is off means inductor doesn't like changing the current.
Yeah.
Then it will induce a back EMF. So that's called the back EMF.
Yes.
Then what will happen is this will become negative, this will become positive. Yeah. So that's what I have shown. So when this becomes negative, this will become positive. It is kind of a cell. And then when this becomes negative, this will become positive. So my question is, then this diode will be on.
Yes.
When this diode will be on, then what will happen is your current direction. And which way the current should flow?
Towards this. The clockwise.
Yeah, the current is, I think the arrow is, I think that's correct. Yeah, the current will be like this.
Yes.
Yep.
So the direction.
Yeah, this arrow is correct. Yeah, the current will be like this. Because if this is other way, then it will become negative. Yeah, so this current will be like, I'll correct it.
So the arrows are wrong.
Yeah, arrow is wrong. Yeah, still the arrow. Yeah, you're right. Yeah, I'll correct it. You know, the arrow. Yes. Yeah, it's not better. Pulse off, yeah. Pulse off, yeah. On, you don't get anything.
So I can get the polarity of this region, but I don't get because I know when this side is red, right? But how do you know this one's close?
Our assumption is we got some from the previous cycle. We got some charge maybe here in the capacitor. You know what I mean? Yeah. Otherwise it will be zero. So that's otherwise if I don't put positive here, people will say that no, there is a capacitor it will be holding some charge. Then I also from arrow I have to correct it. So if we go back to the buck one. Yeah, the buck. No. So, yeah, so this is the this is positive. Otherwise it will be negative.
So on this slide, you said that the capacitor in the discharge is small now.
Yeah, because that's why what I put a positive is from the previous cycle there could be some charge in the capacitor.
Yeah.
That is
Yeah. And so, wait. So does it not discharge when the switch is on?
yeah, little bit discharge will be a little bit.
Okay, so you're just saying that there's only a small
Yeah,
amount of
small
charge in the capacitor.
And also one more thing I need to correct it because in the slide.
So what's the capacitor there for then? Just filtering?
So this one should be other way.
The arrow should be the other way around.
Yeah, it should be like this. Yeah, so coming back here to see the capacitor. There is a very simple. So if there is no capacitor, then you don't have a charge on the ground.
Okay, yeah.
Yeah.
That makes sense.
That's the reason. Yeah.
Alright.
When this one is on in the on state, right? And according to the theory, this one should be short circuit, right?
When the DC current, but then in your case it's not DC. When it is on means your current is suddenly increasing.
Okay, suddenly increasing.
Yeah.
It's open circuit for this one. Can we
No,
see
no,
it's
no,
open
no,
circuit,
no,
right?
no, the current is increased when it is when it is a DC. So you make it. So first case,
in
wait,
the on state.
you make this constantly on.
Yes.
Then what will happen is, then when you are constantly on,
Okay.
then you got a DC current.
Yes.
It is coming and then it is going like this.
Yes.
And then this will be a short.
Mm-hmm.
There is no inductor effect. But
Okay.
when you switch it on like this,
Yes.
what will happen is then your current is, then it is switching on, then your current is suddenly increasing.
Okay.
In that case, then what will happen is this will become positive, this will become negative, the inductor start storing the charge. Because inductor di by dt.
Mm-hmm.
So that will be charging. So that is equal to voltage. So when your current is constant, then you don't have any voltage across the inductor. It's a short.
Mm-hmm.
When I equal to a constant, di by dt equal to 0.
Okay.
But then when the current is varying, is suddenly increasing, then you get a voltage stored here. That's the reason that will be positive and negative like this. This is positive why? Because this is positive, so that is the reason this is positive.
Just behave like the open circuit.
We can't say it's open. If it is open means nothing will pass through.
Okay.
It is storing the charge.
Okay.
And then it is
But
charging like this.
I don't know why this one is reverse bias.
No, because this is negative.
Yes.
So that's the reason this part is negative.
But I think that it's still above the ground point.
No,
right?
this is definitely, if this is a negative voltage, this will be negative voltage.
Why this one is negative voltage?
Because
No, no.
here is charging.
Because this is positive, then it will become, should be negative. Because it's a charge, otherwise
It's
not charging, nothing will happen.
I mean, for example, what I understand, 5 volt, this one is 3 volts, and this one is 2 volts, something like that. Why is it negative?
Something, yeah. So what we, by negative, what we say is it will be less voltage.
Less voltage.
Yeah, but then we can't put in a number, When I put in a number,
Yeah,
that's not a
that's
universal
an example. It's an
Yeah,
example.
yeah.
So
So that this will be definitely